66 million years ago, the most successful animals ever to walk this planet, creatures that had ruled Earth for over 100 million years, longer than we can really wrap our heads around, got wiped out by something they never saw, never understood, never had a single chance against. And here's the part that should actually bother you. We're not meaningfully better prepared than they were. We just think we are. So let's ask the real question properly. Not could it happen again? We already know it can. That's settled. That's history. The real question is, how long do we actually have? And I want to tell you right now, the honest answer is going to surprise you in both directions. Some of it's going to reassure you. Some of it isn't. Let's earn both. Here's the first thing people get wrong right out of the gate. When you say extinction from space, almost everyone pictures the same image, a giant asteroid, Hollywood style, some digital countdown ticking on a screen somewhere in a control room. And look, that's a real threat, but it's only one of at least 4 completely different ways this could happen, and honestly, it might not even be the most likely one. Let's lay them out plainly, because lumping them all together is exactly how you end up with vague, useless fear instead of something you can actually reason about. First, asteroid or comet impacts, the classic one. Second, radiation from a nearby star going supernova, close enough and at the wrong angle to matter. Third, gamma ray bursts, a specific violent flavor of stellar death that fires concentrated beams of radiation instead of spreading energy evenly. And fourth, on a vastly longer timescale than any of the others, the sun's own slow evolution, which, billions of years from now, makes Earth uninhabitable no matter what else does or doesn't happen. 4 different clocks, 4 different mechanisms, 4 wildly different timescales, some measured in centuries, some in millions of years, some in billions. Separate them out, and suddenly the question stops being a single unanswerable dread and starts being something you can actually take apart, piece by piece. Let's start with the one we've actually made real progress on, because I want to give credit where it's due, and this part is genuinely more reassuring than people expect. For decades now, astronomers have been running dedicated survey programs, pointing telescopes at the sky specifically to hunt for near-Earth objects, cataloging anything large enough to cause a global catastrophe if it ever hit us. And this isn't a small side project. It's been steady, systematic, patient work, year after year, and it's paid off. We've found and mapped the overwhelming majority of asteroids over a kilometer wide that cross anywhere near Earth's orbit. Not most of them, roughly. The overwhelming majority, well over 90% of the largest, most dangerous class. And none of them, not one, is currently on a collision course with us for the foreseeable future. Here are the actual numbers, plainly. No dramatics needed, because the truth is dramatic enough on its own. A dinosaur killer scale impact happens, statistically, roughly once every 100 million years. And based on everything we've currently mapped and tracked, we are not looking at one anytime soon. Not in the next 1,000 years. Not in the next 10,000. For that specific threat, the big, famous movie poster asteroid, the sky is about as quiet as it gets. I want you to actually sit with that for a second, because it's a real achievement, and I don't think people give it enough weight. We are not blind the way the dinosaurs were blind. They had absolutely no way to see what was coming. We built the tools. We pointed them at the sky. We did the work. For the biggest, most obvious threat on that list of 4, humanity actually solved the hard part. So if that's the good news, why isn't the whole question settled? Why doesn't this video just end here on a reassuring note and call it a day? Because the quiet threats are the ones we haven't fully solved. And it's not for lack of trying. It's because the physics itself resists a clean answer, no matter how good our telescopes get. Take comets, for instance, a different beast entirely from asteroids. Asteroids mostly sit in stable, well-mapped orbits in the inner solar system, which is exactly why we've gotten so good at cataloging them. They don't move around much. They've been in roughly the same lanes for a long time. Comets are different. Long-period comets can come plunging in from the outer edges of the solar system, from the dark, distant reaches we barely observe at all, and give us a warning window measured in months, not centuries, months. Because we genuinely can't track what we haven't spotted yet, coming in from a region of space we don't watch nearly as closely. Then there's the gamma ray burst problem, which I find genuinely humbling to think about. These depend on beam geometry, which direction the concentrated radiation actually fires. And that's something we simply cannot predict for any specific star in advance, not with our current understanding. We can identify candidate stars. We cannot tell you which way they'll point when they go. And then there's a quieter, less cinematic gap. Smaller, city-destroying asteroids. Not extinction level, nowhere close, but genuinely catastrophic if one hit a populated area. These remain harder to catalog completely, simply because they're smaller, dimmer, easier to miss against the black of space, and there are vastly more of them than the big kilometer-scale ones we've already mapped so well. Here's the honest line I want to draw clearly because it matters. Naming these threats, long-period comet, gamma-ray burst, undetected near-Earth object, is not the same thing as being able to predict them. We understand the mechanisms behind every single one of these. That part of the science is solid. But understanding a mechanism and having a complete working early warning system for it are two very different achievements, and right now we only have the second one for part of the list. That gap is real, and it is not closing anywhere near as fast as most people quietly assume it is. So, how long do we actually have? Let's give the honest shape of the answer, not the tidy one. For the threat we understand best, the big asteroids, the answer is probably a very long time, maybe hundreds of thousands of years, maybe considerably more if our tracking programs keep holding up the way they have been. That's a real, earned, calculated number, not a guess pulled from optimism. For the threats we understand least, the comets arriving with almost no warning, the gamma-ray bursts we can't predict the aim of, the supernovae whose exact timing and geometry we can't fully forecast, the honest answer is, we don't know. And I'd rather tell you that plainly than dress it up as something more settled than it actually is, because pretending otherwise wouldn't be science anymore. It'd just be a comforting story. But here's the turn I actually want to leave you with, because I don't think this should land as pure dread. The dinosaurs didn't get a warning because they had absolutely no way to build one. No eyes turned toward the sky with purpose. No mathematics. No telescopes. No century of patient, coordinated tracking work. They simply didn't have the tools, full stop. And there was nothing anyone could have asked of them differently. We might have a warning. For some of these threats, right now, today, we genuinely do. Real tracking, real data, real confidence. That's not nothing. That might actually be the single most important difference between them and us. More important than anything else our species has built. It's not that we're safe, exactly. Nobody gets to say that honestly about all four of these threats at once. It's that for the first time in the entire history of life on this planet, 4 billion years of it, a species exists that can, at least for part of this problem, see some of it coming and actually do something about it. We're the first living things on Earth who ever got to ask this question in advance, instead of finding out the hard way, the way every other extinction in this planet's history got found out, suddenly, blindly, with absolutely no say in the matter. We don't have a complete answer today. Some of the clocks we can read clearly, and they're telling us we have time. Others are still hidden somewhere we haven't fully learned to look yet, ticking at a pace we can't currently measure. Maybe that's unsettling to sit with. I understand if it is. But I'd rather stand here, honestly uncertain, actually looking up at the sky with real instruments and real data, than stand exactly where the dinosaurs stood, certain of nothing. Not because they were wrong about anything, because they never got the chance to be right or wrong at all. They never thought to look. We do. And that, more than any specific number I could give you tonight, is the actual answer to how long we have, as long as we keep looking.